Hi, everyone. Welcome. Azure Cosmos DB Live TV. Welcome back. I'm your host, Mark Brown. And as promised, we've got Andrew Liu back. Hey, Andrew, how's it going?
Hey everyone, it's really wonderful to be back here, Mark.
Yeah. So back in episode 20, when I first had you on, we talked about a lot of stuff. We talked kind of about the history and evolution of NoSQL as a database and a market. Talked about the history of Cosmos as well, and how it went from a document DB to multi-model, and started getting into all these different kind of aspects of how Cosmos is built. And we, I think, just really ran out of time and had a parking lot of all these different topics we were going to say we were going to come back to. And so now it is, 6 weeks later, and I've got you back on. Actually, 7 weeks, I guess. That was episode 20, and now this is episode 27. So I guess 7 weeks. So I wanted to bring you back and just kind of keep having the discussion. I think it's a good topic, especially, I guess even if you're new or experienced with Cosmos, being a fully managed service, there's a lot of things you don't get to see, right? You don't get into the weeds. You're not provisioning VMs and deploying database engines and configuring replication and networking and all of these different things just to make it work. You go to Azure Portal or you deploy an ARM template, give it a name, give it some throughput, some databases and containers, and that's pretty much, all you need to do. So there's all these things we obviously do for you being fully managed. And I thought, this is a good topic, right? As a developer, I'd like to know how kind of things work behind the scenes so I can understand its behavior and why it does what it does. So here we are. Let's continue our conversation about Cosmos and kind of how it's built.
Yeah, I am super excited. And I mean, as always, everyone, please, bring in your questions. It is a live session. We'll keep an eye out for them. You can put them in the little comments question window, and we'll try to get to them. Otherwise, I'm gonna just here riff with you, kind of give you a behind-the-scenes look at Cosmos DB and kind of what that means to you from a performance and scalability perspective.
Yeah, so where do you want to start? I guess there's the front of the house and our gateway, or the back of the house and the storage.
Yeah, let's jump over to a whiteboard. And I've put together kind of like a parking lot of just some topics that we tried to get to last time. And I know the list kind of grew as we ripped on the session. We'll continue to grow the list, and then I'll try to DQ them as we go. And everyone, please feel free to add to it. But we can kind of make this our rough agenda and list of topics. I figure a nice beginning point would be looking at gateway and direct. And what that is Cosmos DB actually has two connection modes. Effectively, Cosmos DB is a distributed database, meaning it's not just one server. We distribute this across many computers in the back end. And so how we route requests so that, imagine that if a piece of data, Alice's data is on computer A, Bob's data is on computer B, and you run a query, how do we actually go route that query to the right computer? So that's going to set the stage, I think, for the first two topics. Our connection modes, gateway and direct, will kind of demystify our front end and back end. The back end is partitioned, so it'll be a very natural segue, and we'll kind of blur that second topic around how Cosmos DB actually handles scale out. When we zoom in on any particular node, there's also going to be a few interesting aspects like, how do queries work? Once we've routed a request to a computer, like what happens next? There's the other side of scale out. So the two dimensions of scale out you can think of is like, hey, I have a bunch of requests, like queries. I have a bunch of data. It doesn't fit on a single machine. There's actually two ways to scale that. If you have a ton of writes and you have a ton of data, I mean, easy way to handle this is you load balance, right? Like you get two computers and you put half the data in one computer, half the data in another computer, and you load balance the requests across those as well. That's called partitioning. But what if I have the same piece of data that is also getting read very frequently? You can both scale that through replication and get more reads by copying that data as opposed to dividing that data. And then the other thing you can do is as you copy that data, there actually are a few other motivating reasons, especially around availability, high availability. It gives you a lot of redundancy when you do this, which is very good for mission critical applications. And then if we have time to it, I'll get to another topic, which is the Cosmos DB change feed. I think this is one of the most powerful features. It's a very simple feature, and I think it often gets overlooked. But in terms of the design patterns and how you implement things like event sourcing or materializing views, it's an incredibly powerful primitive for developers to go and implement some of these very advanced design patterns. And so
that looks like a good agenda, and we've already got a comment here. So Tom, I love behind the scenes talks. So I think,
wonderful.
So
let's dive in.
Yeah.
So I'm gonna get some whiteboard real estate. Let's demystify the gateway first. So Cosmos DB effectively has, well, maybe let's break it into like the lifetime of a request. We have basically things that, from a database perspective, it would be the database client. We have things that basically have a front-end view, which is how we route requests. And then we also have a back-end view on how we look at it. And so the client actually can be multiple different things. Let me, front end. So effectively, the primary way to interact with Cosmos DB is through our SDKs. We have a variety of different APIs, and no matter which API you're using, whether it's the core SQL API, the document API, the Mongo API, the Cassandra API, Tables API, Gremlin API, your application is going to connect to it through some form of SDK. Alternatively, you have an HTTP client, and that's actually what, depending on which API, it's going to have different protocols. But think of it as like a HTTP client or a TCP client that is ultimately making the request. And that goes into, well, this mysterious cloud endpoint, right? Like the cloud endpoint we expose will be that connection string. And if you're using the core SQL API, it'll look something like a, well, there's a REST API hidden behind that. And if you're using some of the other APIs, like, for example, Mongo API, you're actually just talking over like a raw TCP stream where you have some bits. The bits will be something like an opcode, and the opcode will tell you, oh, this is a create versus a query. And the following bits, of course, will be based off of that opcode. Like if it's a query, the following bits will be something like, well, here's what the query is. Here's the filter predicates, and here's what we want to project. So that goes into this thing called the gateway. This is what we like to call it. But effectively, this is just, you can almost think of it as, it does two jobs. It does our interoperability. This is what powers all of our different APIs. So when you're making a Mongo request, a Cassandra request, a tables request, a Gremlin request, a core SQL request, Cosmos DB doesn't actually have like 5 different databases in the backend. It has one common platform, one common backend in the back. The core SQL API is actually the quote-unquote native API. It's what our backend speaks. And so what the interop layer does is it basically does a live translation. When you're running a query, whether it's through the Mongo driver, the Cassandra driver, the tables driver, Cosmos DB goes, oh, OK, queries. I understand how to do queries. So you pass in a Mongo query, and I'll translate it into something that Cosmos DB understands, a Cosmos DB query in the back end. And we actually host another little client in the back end that's using direct mode in the back. And what this does is actually federates that request to a partitioned backend. And so when you look at the backend, you can think of it as a bunch of, or maybe I'll kind of explain, there's a hierarchy here. We have these things that we like to call partition sets, or in our documentation, I believe these are called physical partitions. The thing to note about a physical partition is it's actually not one server. It's actually a replica set. And so within the partition set, we actually create these things called replicas. And what we do is we do a little set per region, so that if you have multi-region configured, like if you have a 2-region or a 3-region or n-region Cosmos DB account, what we're actually doing is within that quote-unquote physical partition, we're setting up these database replicas. The database replicas where we actually host the Cosmos DB software itself. This is think of it as a query engine, an indexing engine, a storage engine. And so that's what actually does all the magic of, hey, I want to write a piece of data, I want to read a piece of data, like bread and butter, what a database does. That is hosted within a replica. And what we do is we distribute this workload across many, many replicas. So think of it as I have a replica set. Imagine like I have, just for sake of example, 4 computers. And whenever I write a piece of data, let's say I'm going to use one piece of data is going to be the color red. We're going to replicate that data across a replica set. And if this is the first region, let's say this is West US, and I have a database account that's also configured in East US. And we'll just, I mean, it can be any region, but just using an example. What we effectively do is the SDK will say, hey, let me write that request. The gateway is going to route it to a particular partition. And that partition, let's say if I'm writing the piece of red data, this is saying insert red. What we're effectively doing is writing it into one region. And then once you write it into one region, what we also do is establish replication across these regions, where one of these nodes within the replica set is designated a forwarder, and that's what is going to coordinate their replication. Things get a little bit more complicated when you start looking at multiple write regions, when you have active write topologies, because you're no longer just forwarding a piece of data. If I have 2 conflicting writes come in, then let's say at time is 10 a.m. and exactly at 10 a.m., let's say across West US and EUS, the network latency is about 50 milliseconds. Within that 50 milliseconds, if I try to write 2 pieces of information, like let's say the record I'm modifying is an apple, and I'm saying the color is red in region 1, the color is green in region 2. We also have to do some things around conflict resolution so that way you converge. You don't want a situation where in one region, the color, that record is a value red, and another region is a value green. We'll go into that rabbit hole a bit later. For the time being, we're going to simplify the discussion and first talk a little bit about the just what happens with the client, the front end, and the back end, and how that overall topology looks like. And so this is going to be, let's say, whoops, let me change the color. Can I just, yeah. This is, let's say, partition 1. We also have n number of partitions that are forming these replica sets. And what this allows us to do is scale. Like if I have, let's say, an arbitrarily high amount of information, let's say a petabyte, that I want to store in Cosmos DB, well, unfortunately, we can't store a petabyte in one machine, but a petabyte can be subdivided. And so what you're doing is you're just subdividing that data until it fits onto a machine, and you're having many of these partitions that effectively go and each have a fragment of that data, so that cumulatively you can store that entire petabyte of information. So this is going to scale to n number of partitions, and I'll kind of talk about how we actually end up routing. Like when we write a piece of data, let's say the red record, and then later on the blue record, how do we know that the blue record should go to partition 2 versus the red record should go into partition 1? And you want this to be deterministic. Why this needs to be deterministic is if I write, let's say, a piece of data to partition 1, later on when you query that piece of data, if I query that on, let's say, partition 2, well, it's not going to find the information. That actually needs to go back to where I've written it.
Sure.
And so this does need to happen in a very deterministic manner. And so we have an algorithm for this. It's a fairly common algorithm. Pretty much every distributed database standardizes on it. And this is an algorithm called consistent hashing. And this basically is how we deterministically can write to a partition as well as locate that data to read from that partition. Imagine that I have a number line that goes from 0 to maximum value. And I have a hashing function. This is the hash part of a hashing function. Every single value, if you feed in a value, let's say Alice, Bob, and Carol, these are going to hash to somewhere between 0 or min value to max value, right? So Alice might be here, Bob might be here, and Carol might be here in terms of the hashed value. Now, what we do here is you actually have a challenge here. And the challenge is let's talk about naive hashing, and then we're going to evolve that into consistent hashing. So let's talk about naive versus consistent hashing. And why this is important is a concept called elasticity. Not only do we want to scale a database, which is to distribute that workload across, let's say, a cluster of many machines, but what we also want to be able to do is elastically grow that and shrink that so that that way we can manage our costs. If we grow or we're stuck, then, I mean, it puts ceilings on our scalability. Elasticity is that property that the workload can continue to grow and shrink and fit that as needed. Cosmos DB, of course, manages that and needs a mechanism to go and learn how to manage that. So if I look at a naive hash on those values, imagine if I did Alice, Bob, Carol, and on the naive side, let's say that hashed to some number, and we're going to mod it to number of partitions. And that way we can say, hey, regardless of what you hash to, we're going to fit you onto a set of partitions. So let's say we have a number of partitions initially is 2. Then we can solve the scalability problem by just going, OK, Alice will go to machine 1. Bob will go to machine 2. Carol will go to machine 3. What happens if we need to grow from 2 to 3 partitions? This is where it becomes problematic. If on random distribution, we have something that looks like 1, 2, 1, 2, 1, 2, and I now need to move to something like 1, 2, 3, 1, 2, 3, what you're going to notice here is there's a lot of wasted movement. We have to move values. Let's say when I expand this out to Danny and Eve, Carol is moving from machine 1 to 3. Danny's having to move from machine 2 to 1. And Eve is having to move from machine 1 to 2. This isn't very efficient. And so this is why we don't use a naive hash. A naive hash is not what we want. Instead, what we do is we do a different algorithm called a consistent hash. And so the way consistent hashing works is, remember that number line we were talking about? Think of that as just project that out to a circle where this is min value and this is max value. Just like a clock, once you hit max value, you just roll over back to the min value. And what a consistent hash does is it actually mixes 2 concepts. Rather than just hashing, it also uses an additional layer of abstraction called range partitioning on top of that hash partitioning. And so given I have a set of hashed values where Alice might be here, Bob might be here, Danny might be here, and Carol might be here, is initially if I had a need for 2 partitions, what we do is we just straight up divide that number line so that that first half of hashed values go to, let's say, machine number 1. And the second half of hashed values go to machine number 2. Now, here's where consistent hashing really shines, is the elasticity problem. Imagine that machine 1 is now filling up. Like Alice's data and Carol's data is actually a lot heavier than what we had expected. Or perhaps we have even more users on board on, let's say, our let's say we've made a social media platform and it's going gangbusters. Like the number of users has really started to pile up. And we now have, let's say, billions of users all over this ring on where we're hashing them to. Well, the very easy thing to do is you go, well, let's split that partition. Let's say machine 1 is filling up. So what we do is instead of having one machine carry the workload, we can have machine 1A and machine 1B. So in total, we have 3 partitions. The nice thing here that you're going to notice is this doesn't require any data movement. I'm not having to move data to machine 2 or pull data from machine 2. A partition can actually, in isolation, split itself and elastically grow. And later on, if machine 2 needed to split as well, same thing, machine 2 can become machine 2A and machine 2B. And what we can do is we can actually subdivide these rings to n number of subdivisions. Think of it as like a pizza pie. And that pizza pie, I can just keep slicing and subdivide a slice to meet as many consumers as I need. And this is effectively how we're dividing up that data. And because we have a very deterministic way of locating this information, like if I hash a value, later on when I want to query for, let's say, Alice's information, well, when I hash Alice and say, oh, Alice hashed a value, let's say, value 1,356, just for sake of example. Well, when we go and look at the ring and say, oh, OK, well, this goes to 0 to n on this partition, and the next partition has a range from n to m on hash values, and 1356 actually hashes to a range between m+1 and value o. So therefore, when you run a query, you don't need to go and just like figure out or fan out. There's a category of queries called Fanout Queries. A Fanout query is, I don't know which partition to route to, so I ask all of the partitions and ask them to check their index. In this case, since we can deterministically say, oh, you know what, because we have a locator, a placement hint, route that query efficiently to just the one partition that's relevant to me. Now, how we go and implement our consistent hashing is, notice we need a value to hash. And what we end up doing is when you create a Cosmos DB container, whether that's a collection, a table, a graph, and our various different APIs, we always ask you for this thing called a partition key.
And people complain about it.
People ask, like, what the heck is this
why
partition
do I
key
need
thing?
that thing? Yeah.
Why do I need to know what this is? Well, effectively, a partition key is the placement hint. When you tell us that, hey, I want to partition my data by, let's say, users, so I set my partition key to the user ID. Well, what that says to Cosmos DB is, OK, now I can deterministically look at the user ID for every single record, run through this consistent hashing algorithm to both route the writes to the right computer, as well as the reads. I can also route those to the correct computer. And what ends up happening is, because we use the partition key for this, you want to put a lot of care and thought in your choice of partition key. Basically, there's a set of design time problems, and there's a set of runtime problems. The runtime problems are the things that Cosmos DB solves. This is the, how does routing happen? How does growing or shrinking to provide elasticity? How do these things happen? The nice thing is Cosmos DB takes care of you for all of the runtime. So this is like taken care of by the system. But at design time, you still need to define a partition key.
Yeah.
This is what we ask from our users to do.
And it's one of those things where we front load a lot of big decisions on users when they get started with us. And I see users constantly kind of tripping over this because they've got to think about this at some depth before they can really do anything. But it's, but but if you do put that time into it, I mean, look at what you get as a result of it, right? So
yeah. So an important thing to call out here is it's not a unique thing to Cosmos DB. This is a fairly general principle for scaling out. The observation I noticed is scaling applications is a lot easier than scaling data. The reason why that is for scaling an application, what you're typically taught is make the application stateless. And as long as we make the application stateless, I can go spin up another virtual machine, deploy my software, whether that's in a virtual machine directly or through Azure App Service or through some containerization software, let's say Kubernetes. And what I do is I just quickly spin up a computer, put my software on it, and hide it behind that load balancer. And what we do is we can randomly load balance across these machines. The problem we have on the data side is, well, it turns out applications, as much as we want them to be stateless, it turns out state really, really matters. When we go and scale our app and say, hey, OK, it's stateless, things are great. Imagine I'm building a shopping cart. My shopping cart might be stateless, but ultimately, if Alice goes to your website and adds something to the cart, and then later on goes to checkout, and you go, oh, yeah, you know what? It was stateless, so I have no idea what's in your shopping cart.
Yeah, what are those other things that they added earlier?
So it turns out state is really, really important. All we've done is we've punted the problem. Where have we punted that problem to? Well, we've punted it to the database.
Yeah.
And we've gone, hey, database, I'm going to dump all of my state on you. And application, just don't worry about the state. The database will handle it. We'll run a query, and it'll tell us what the shopping cart contents are. The challenge is that databases, well, they need a way of also scaling out. So if you, as much as you scale out your application, if you home all of your data on a single computer in your database, well, your database very rapidly becomes the bottleneck. And so the database also needs to scale out.
Yep.
And so what ends up happening is these are design patterns that actually they're not fairly new. Consistent hashing is actually a very old algorithm. If you've ever had to, like, if the year was 1995 and we were still using everything, like the world revolved around relational databases, well, guess what? You would go and manually shard across your relational databases. You'd set up a relational database for, let's say, part of your data set. If I needed 10 shards, then a tenth of the data set and in each one of these instances. The challenge there is it's not just a design time problem anymore. It's also a runtime problem. Your application needs to solve the routing, and your application needs to solve the, oh, crap, what if I need to grow from 10 shards to 11 shards because it turns out business is doing very well and we need to grow. And so these are not novel problems. I do think these are problems that, as time has gone on, the nice thing in 1995 was, I mean, I still remember the days of just writing plain old HTML websites. The web was very simple. It used to be static. The whole concept of like DHTML and having some dynamic content on your website was still fairly new.
Giving me terrible flashbacks right now.
This is like pre-JavaScript days, or JavaScript was very simple. The concept of AJAX, of asynchronously making calls to a backend and having dynamic content, unless you were like really truly like a thought leader, it just wasn't a mainstream concept yet. Fast forward to today. The observation is, well, web is very dynamic. It turns out rather than having a static, let's say, a product catalog, things like real-time personalization can really make that catalog pop a lot more, like actually surface the things that are relevant to a shopper as opposed to not relevant to a shopper. And how we personalize that is, well, it turns out we need to know a lot of information about our user. And fast forward to now is like, oh, well, we have scalability challenges have just become mainstream, is the observation. And it's not just in retail with like real-time personalization. It's things like in manufacturing. Turns out when the assembly line halts, it's really, really bad. So we want to do things like predictive maintenance and keep the assembly line online. But in order to do that, every machine is now like producing a heartbeat and a bunch of telemetry. And once again, it's like, wow, that's a pretty gnarly scale problem.
Yep.
Anyhow, long story short is partitioning is the key to make this happen. And I will leave the partitioning conversation with just a few design principles. And these design principles are your guiding light on, hey, there's really confusing and new novel topic around partitioning that has been thrust upon me. How should I actually rationalize and think about this? Design principle 1, you want to pick a partition key. Let's scope this to picking a partition key. Design principle 1 is you want to choose a partition key that is able to distribute your overall workload. And what you want to do is you want to efficiently load balance your workload across as many computers or as many partition key values as possible. The second design principle that I want you to think about is how to efficiently route the majority, keyword majority of your requests, especially your query patterns. Ideally, a query can be efficiently routed. And if it can't be efficiently routed, like imagine if I don't have the partition key in the query. If I say a use case had partition on user ID, when I run a query select star from this collection where user ID equals Alice, we know where Alice's data is. But when I run a different query, select star from this collection where age is greater than 30, well, it turns out that Alice might be greater than 30, Bob might be greater than 30, Carol might be greater than 30. Only way to find out is you do this thing called a fanout. Fanout is not necessarily a bad thing. When you're doing ad hoc queries, I guarantee you're not going to find, like if I enumerate every single possible query you're going to run, you're not going to find like, oh, I have the exact same where clause in every single query. My where clause tends to differ. But what you want to do is you want to get the majority of your queries efficiently routed. And the reason why is doing a fanout query on its own, like one fanout query or 10 fanout queries, isn't really going to make or break an application. They actually can be done in parallel. So the performance of that individual query is actually still pretty good because we can just ask all of the partitions in parallel. What really hurts is when you are in a situation where every query fans out. So if my goal was to scale, let's say, a million requests per second, well, if every machine has to scale to a million requests per second, that's not actually going to work. The way we actually scale a million requests per second is we subdivide it. And fanout actually goes contrary to our ability to subdivide. So like if I had a million requests per second going on, ideally what you're doing is something like, oh, 10,000 will go to machine 1, 10,000 will go to machine 2. And what a fanout does is it's actually pushing, instead of dividing that, you're just running the million on every single machine. You have a scalability challenge again.
What do you say to someone that is designing their database and their model, and they're like, hey, I ran all these queries in Data Explorer, and they didn't really cost a whole lot in RUs, but 6 months, a year later, I'm running into problems.
So the thing you want to do is during initial development of a brand new application, the amount of data and the amount of traffic you have is still low. But once you hit production and people are actually using the system, that's typically where you go like, oh, it turns out that running one query versus running a million queries at any given point in time is a very different story. What you want to do is you want to try to figure out ahead of time which of the queries are going to be your common queries. Like given 100 different queries, what you find is a minority of those queries actually end up being the majority of the workload. Like if I go and enumerate out query 1, query 2, query 3, all the way to query 100, what you'll see is there's like this Pareto principle, the 80-20 rule, where 20% of your queries, or it's actually usually even more drastic than that, but a minority of your queries is actually the majority of your traffic. Like when the application boots up, I'll use a product catalog for a sake of example. You show your aggregate product listings a lot more often than certain details pages. Like people tend to browse around. And so when I look at these 100 queries, you're going to find like, oh, these are the 3 queries that keep getting run over and over and over. And so what you want to do is you want to optimize around those. If query 100 is infrequently run, fine, just let it fan out. But if query 1, 2, and let's say query 4 or the ones that are constantly being peppered on the application, those are the ones you're going to want to optimize around for the partition key. The way to get clarity on this is try to figure out, like, do you understand how your application is being used?
Yeah.
If it's a shopping cart or a product catalog, well, you can intuitively think like, well, common operations are, give me the shopping cart for Alice, give me the shopping cart for Bob. What's not going to be very frequent, and users typically don't do, is find me all of the shopping carts for people between the ages of 30 and 35. You might have a business analyst who is interested in that kind of information. Maybe they're using that to do some very important business decisions. However, you might have 1 million shoppers at any given time. You are not going to have 1 million data analysts in any given second asking you that question. In fact, you probably have a much smaller team. If you have 1 million data scientists, like, wow, that's amazing. But most companies actually have like, well, it turns out instead of 1 million, I might have a team of 10 data scientists. And instead of running a query per second, they're actually running like 5 queries per hour. So if I translate that to queries per second, it turns out that it's less than 1 query per second. Meanwhile, my live website,
they're also probably not running it in the OLTP data store if they're a data scientist,
in fact,
too, right?
You bring up a very good point. Your data analyst honestly has other tools available. And a beautiful thing that Cosmos DB has is a completely different other feature called Synapse Link. And you can use a purpose-built query engine that is a bit more purpose-built for analytics. Basically, this actually might be a nice segue into, I believe our next topic was query. So I would broadly put queries into 2 buckets. There's OLTP queries and there's Olap queries. What the difference between an OLTP query and an Olap query is, when you look at your transactional, the T in OLTP stands for transactional. When you look at those queries, typically what you're doing is you're doing a ton of them. It's like what your application, your live website is doing. Like, hey, give me the shopping cart for Alice. Now give me the shopping cart for Bob. You want lots of small requests, and these tend to be needle and haystack queries. Like, given 1 million users, I honestly don't care what the like Alice really doesn't care what's in the 999,000 other users' shopping carts. She just wants to know what's in my shopping cart, because that's what I'm going to buy. I don't want to buy other people's stuff. I want to buy what I chose. That's a needle and haystack query.
I always leave my Amazon wish list up, though. So if people want to.
You'd probably love for everyone else to buy and send you stuff.
Sure. Send it my way.
Let's kind of capture this and codify this. Let me give some board real estate and looking at queries. OLTP queries versus Olap queries. And why this is important is you optimize them very differently. These tend to be highly concurrent. There's lots of them going on. And they tend to be short-lived. These are things that tend to, they're actually pretty quick. Like when I do just find me when it's in a shopping cart, it's a relatively simple query. The latency, these are latency sensitive. If my shopping cart took, let's say, 1 hour to load, well, I'm pretty sure your user bounced like 59 minutes and 59 seconds ago. Too late. No one's gonna sit there and like wait for your shopping cart for an hour to load, unless like you have something really, really compelling, like a PlayStation 5 or a new graphics card, things that are in hot demand and in short supply. Most people just honestly aren't going to put up with it. If you're just selling like T-shirts, by the time the shopping cart loaded, I bought a T-shirt on another website. Sorry, I'm gone. Olap queries, on the other hand, they're compute dominant. And what I'm doing here is, rather than giving me Alice's shopping cart, I want to do some analysis, right? These are your typical analytics. That's the A in Olap is analytics. A key thing is these tend to be scans, and OLTP, these tend to be seeks. Seeks are, hey, given a terabyte, let's say, data set, I only want a kilobyte of information, and I want you to find that kilobyte. It's a needle and haystack, very, very fast and very, very efficiently. In contrast, for the Olap, a lot of times is well, I actually want to just go and group by, like I want to find, let's say, sales patterns by age demographics or by geography or by a certain set of dimensions. These tend to be scan queries where I'm going to read every, like a majority or a very large chunk of that terabyte, and then do some batch computation on top of that. And so the main thing you want in a seek is this thing called an index. Whereas when you do a scan, honestly, whether you have it in index or not, if you're going to scan everything, an index will help. Like if you are only caring about certain dimensions, it can narrow the data analysis. But at a macro level, it's not nearly as important to optimize that as aggressively as an OLTP query. So there's a bunch of different characteristics difference. And then there's how do distributed systems optimize for them? When we look at or scale out systems, one key differentiation here is how do we manage resource governance? When we look at resource governance, if you're going to tell me I need to, given like I have, let's say, a cluster of finite CPU that I can keep scaling, but nonetheless, whether I have 100 nodes, 1,000 nodes, they still have like a number of CPUs, and those CPUs do cost very real money. Should I, if I have 1 million requests, well, then maybe I should be very frugal on the CPU, memory, and I/O. So you want to be frugal per request. And by being frugal per request, what you're effectively doing is it allows you to run lots of these requests in parallel. You're optimizing for parallelism. Optimizing for parallelism at a workload level, not at a query level. Workload.
So this is managed at least how these things get distributed at the gateway level, right? So when query hits the gateway is distributing the query. It knows which physical partitions to go hit because it knows where the data is, maybe, if it's passed in. I guess if it doesn't, it goes.
Yeah.
And then
I guess what I'm
all
trying to allude here is, should I run analytics directly on Cosmos DB's OLTP service area? Or should I run transactional workloads on my data warehouse? And the answer is, it's not going to work well. And there's a very good reason why it doesn't work well. And it comes down to the architecture, specifically how these systems handle resource governance when they scale out. So when I have millions of requests, what Cosmos DB does is it tries to reduce the amount of CPU, memory, and I/O per request so it can run all of them. In contrast, if I only have, let's say, a team of data scientists who run, instead of 1 million requests per second, they run 10 queries per hour, you want to parallelize the request itself. My spelling is not very good. Parallelize the request itself. And you're optimizing for a different thing. You're optimizing the latency for a very compute-heavy request.
This is why MapReduce is so popular in this space.
Yep. MapReduce is the core primitive on how pretty much any modern data warehouse or big data system works. When you go and run, even if you're not writing maps and reduces, you're running, let's say, select star from where group by, and you're doing a sum, average, min, max, whatever math you want. What effectively happens behind the scenes is you turn that query into a set of map and reduce steps that run in the back end.
Yep.
The main thing is, like, given a pool of compute, do I give all of my compute to this one request, meaning I can't really run too many of them in parallel because I've parallelized the request itself? Or alternatively, do I try to minimize the footprint on each request so that I can run just a ton of requests?
Well,
and that's the fundamental difference.
And that's why those things are job-based as well, right? Because they're long running. They're going to hit lots of machines. There's lots of coordination involved. I mean, I see this with like the old scope queries, I guess, but that old I guess you call it.
Yeah, whether you're running MapReduce, Hive, Pig, Scope, uSQL,
it's all
Spark
the same.
SQL,
You write your query,
Honestly,
you
a
stuff it
SQL
in a
query
job.
on SQL Data Warehouse,
Yeah.
Synapse, it's all the same,
All the same.
more or less what's happening at a high level. There are some, when you zoom in, there are differences across these systems, and a lot of intellectual property built up over the years. But they have some fundamental, like at a broad category level, fundamental differences between transactional and scale-out systems. Like the type of things I would run in a data warehouse or on something like Synapse, it looks very differently from what I run in Cosmos DB. And you really want to use purpose-built tools. Otherwise, it's kind of like the metaphorical trying to hammer in a screw. It just doesn't work very well, and you probably should pick up a screwdriver. Maybe if you hit the screw as hard as possible, the screw will still go in as if it were a nail. You'll probably like tear all of the threads in the screw hole. But it's not an efficient way to go about things. So let's talk a little bit about zooming in on the OLTP side. I think both sides, there's a lot of depth. It's a rabbit hole. In Olap, it's actually not just batching. In the analytics side, there's actually subcategories like how to do batch analytics, stream analytics, interactive analytics. And then there's different, like just within Azure, we have different ways of handling that. Like if you wanted to do batch analytics, Synapse SQL, and writing a Spark SQL query on Synapse or Databricks can work very, very well. If you're doing stream processing, well, maybe you should be looking at Azure Stream Analytics. It's a more purpose-built tool there. And likewise for interactive analytics, you'll find that these things are a lot more responsive. You're not waiting like an hour for a query to come back, but they put boundaries, like very tight boundaries on what you're able to accomplish. This is where Azure Data Explorer, Log Analytics, Time Series Insights actually do very, very well.
Yep. You want to talk about our, since we're on query, you want to talk about our indexing?
Yeah, let's jump into indexing on the OLTP side. Cosmos DB actually has a fairly interesting way it approaches indexing. Imagine that I have a table. And whether it's a table or JSON, it actually doesn't make a huge difference. Imagine that if I had, let's say, a table that had like a person's name, like this is Alice, it has her age, 30, it might have an address, etc. Let's say Alice lives in Seattle. The traditional way that we used to build indexes is, let's say I'm querying on the name and the age a lot. Well, what I end up doing is I create a B tree here and a B tree here. And these are two independent trees. And so this brings us to the legacy of the whole like alter tables, create index type of management. This is the classic index management behavior. In contrast, there's actually another approach here. The other approach I want to show is this thing called an inverted index. And there's some nice things that inverted indexes bring. I'll first maybe talk about the pain point. The pain point I have normally with traditional index management is as I grow my cluster, whoops. Well, interesting. Let me scroll up. Remember that we've now sharded our database into many little computers. Imagine, actually, a very easy way to simplify this problem is let's go back to something that everyone understands well, relational databases. How long did it take to run alter tables create index? Now, if I have to magnify that, I have 10 database shards times 4 replicas, 40 computers. And when I do alter table create index or add a column, well, these things take a while.
Yep.
And during that time, you can't actually have your application smoothly operate. Like if I have a data model on my application that's expecting, I've built a new feature, I've added a new property, just doing alter tables, create the column, and then alter, or also create an index on that column. Until that is completed across every single one of these shards, every single one of these replicas, the application at the time has to just kind of sit there and wait. And so the way we used to handle this is you'd have like some kind of like Patch Tuesday you would go, hey, everybody, we're taking our website offline for maintenance. And then we'll be right back, 6 a.m.
Yeah.
On the next business day. The challenge here is when you look at modern workloads are very sensitive to downtime. It turns out that, hey, when I take my shopping cart offline, well, it's a lot of revenue loss. All the order flow is just stopped. And during that maintenance period, especially I'm selling goods that are not unique to me, if I'm selling something that's available in someone else's product catalog, well, crap, I just missed out on a whole lot of traffic there. How do I solve that problem? Well, let's look at fundamentally what's happening. What's fundamentally happening on the is every single shard and every single replica is going, I am the source of truth for what the data model is. Meanwhile, every single instance of your application is also going, I am the source of truth of what the data model is. So I have, like, let's say 10,000 sources of truth. And if they don't match, the application doesn't run. Well, can we think about a better way to handle this? And the better way to handle this is, can we not have one source of truth? We'll just make the application itself authoritative. Whatever the source code for the application has, that defines the data model, and I don't have to align a bajillion other things to try to resolve that discrepancy. So this is the birth of flexible schemas. Flexible schemas does not mean schema has gone away. Flexible schema means from a management perspective, you can actually keep your workload online when you have highly distributed systems. And so this is what an inverted index brings to the table for how do you handle flexible schemas from an indexing point of view. So rather than having, let's say, a B tree per column and having well-defined columns like name, age, address, and later on tomorrow, if I add zip code, let's say zip code is the new kid on the block. In terms of what column we want to add, rather than doing alter tables create index and also adding the column, an inverted index is flexible. And the way an inverted index looks like is, let's talk a little bit about like how Cosmos DB views data. We've actually embraced fairly heavily a few different data models. For sake of simplicity, I'm going to focus a little bit on the document-oriented data model. But a lot of the concepts here are going to translate across a lot of the different NoSQL data models. The neat thing about a document-oriented model is it's self-describing. Like if I look at JSON at this point has become fairly ubiquitous. Every single record actually tells you what is its schema. And so rather than having table-level schemas, you actually have record-level schemas. The record itself will tell you, I have a name, I have an age, I have an address. And for one instance of this, I might have, let's say, Alice. By having Alice, it's actually telling you several key things here. Not only is it telling you what the value is, it's also telling you its data type. It's a string. If its age is 30, and I'm telling you, it's a numeric. And this can get complex. Like if I wanted to embed an address and have, let's say, the street, zip code, city separate, we'll add these just for sake of example to show the shape of an inverted index. We can say the city is, let's say, Seattle, and the zip code is 98101. In contrast, we also have Bob. Let's say Bob is 35. And he lives in Los Angeles. And his zip code is, I honestly don't know what the zip codes are over there. 1, 2, 3, 4, 5.
I know what mine is, but I don't know what they are up in LA. 9291 something, I don't know. So, yeah.
So let's say this is record 1 and record 2. Now I want to run a query. My query says, in this data set of 2 records, find me users whose age is 30, or find me users who live in zip code 98101. What an inverted index looks like is as such. There's a logical layout and there's a physical layout. We're going to talk about the logical layout to build the intuition on this. We first have this thing called a root. The root actually has a pointer. The pointer in this case is going to have a pointer to records 1 and record 2. Underneath that root, it's actually yet another tree. It has this thing called a name. And under that name, it's going to have both Alice and it's going to have Bob. Bob's going to have a pointer to record 2, and Alice is going to have a pointer to record 1. Likewise, name is going to have a pointer to records 1 and 2. As the new records come in, let's say tomorrow I add under another property address. Let's say historically address has a city with Seattle and Los Angeles. Seattle might point to 1. Los Angeles points to 2. City points to 1 and 2. Address points to 1 and 2. The type of queries you can run are, hey, find select star from this container where, let's say, the name property is defined. Well, what we would do is look in the index and see, oh, name property is defined. Well, in the query results, we should go and surface documents 1 and 2. So therefore, we're going to see both Alice and Bob come back in the query result. If I do a query select star where the name is Alice, when we look up Alice, well, Alice points to record 1. So in the query result, we're going to surface record 1 in the query results. Now, what's neat about an inverted index is you're not explicitly defining it on a per property or per column level. Tomorrow, let's say, just for sake of example, Alice, we didn't even define what a zip code is. But for Bob, we did define a zip code for the very, very first time. This is from an app development perspective. Tomorrow, you've added a new feature. It needs a new property. Well, what the inverted index does is it's very dynamic. It just goes and adds another path. Oh, I have a zip code. Well, the things that I have a zip code defined for is record 2. And that zip code of 12345, that also points to record 2. And so what happens is when you run queries, what we're doing is we're just adding new paths to the tree. And without any index management, like alter tables create index, the tree can just automatically populate itself. That isn't to say that you shouldn't optimize an index. You should still optimize an index, because if you have a document that has, let's say, 1,000 properties, it turns out if you only query off of 10 of them, it's very wasteful to generate on the table 990 other entries. However, it's not as it becomes a optional optimization as opposed to a mandatory deployment step.
So does that get expensive from a storage perspective? Look at this. There's a lot of stuff getting stored in here.
So this is the interesting thing is what we found. We've done an analysis. When you look at typical documents in a collection, most of them actually end up having the exact same properties. Like it turns out that if I have a shopping cart, what are the chances if document one had the property name, that document 2 would also have the name of the shopper? Well, that likelihood is very high. And so when we look at a property level, there's a very high degree of overlap. And because there's a very high degree of overlap, the actual additional overhead, imagine that I insert document 3. All I'm doing in the tree is adding the value 3 into the pointer. And so this is highly compressible. We actually play additional tricks on the physical layer. So once we have this logical layer on what a logical tree looks like, on the physical layer, what we do is we do a bunch of bit manipulation. So those pointers are actually really big bitmaps that we can do a lot more optimizations around. But in practice, because of the high degree of overlap that you tend to have across documents, even if they don't have the exact same schema, most of the properties are overlap, that the index overhead in practice actually isn't too high. I would say in practice, if you store, let's say, a gigabyte of data and you turn on automatic indexing, on average, I would see something like 400 megabytes of additional indexing overhead. So it's like 40% more for indexing every column, every property. And you can then further optimize that. Where this becomes problematic is if I have 1,000 properties and I only query 10 of them, that's only 1%. And there is an RU charge for generating all of those index properties. So rather than looking at the storage footprint, you should actually be looking at the RU overhead. And at some point, if you go like, well, it's only 0.2 approximately RUs per index path, At auto indexing on 20 paths is what, 2 RUs? Okay, not a big deal. Auto indexing on 1,000 properties, okay, now that's 200 RUs. If I only need 10 of them, I should probably optimize my index policy. So that's how you want to think about indexing here. I would encourage people to optimize, but I would also point out the nice thing is it becomes an optional property as opposed to a mandatory deployment hurdle. And that at a high level is how indexing works. There are some other nuances. The specific nuances that I would say that are also good to call out are geospatial indexing and composite indexing. Geospatial and composite. I think geospatial indexing is a pretty deep rabbit hole on its own. There are ways of handling it. Basically, there's this thing called geohashing, and you can basically do this thing called quad trees, where you think of it as like, if I have, let's say, a map here and I have a coordinate, you can like subdivide each of these into coordinates so that you know that it's like this part of the tree, this part of the tree, and this part of the tree. That's at a high level how quad trees work. To go and quickly narrow down a bounding box or a distance query. I won't go too much in depth because just from a timing perspective, I think we might be running up against an hour again.
Yeah, that's all right. It's my show, and I don't have to worry about any show coming after me. I pretty much.
Oh, wonderful.
Yeah,
well, we'll go over a little bit then.
That's fine. Yeah.
My takeaways here, actually, composite indexing is the more important one. Where composite indexing becomes applicable is when you have things like where A as a condition and B, or alternatively, like where A order by B. What ends up happening is Cosmos DB can go and check the inverted index for A. It can check the inverted index for B. And what it does is it does some set theory behind the scenes. Like if I'm doing where A and B, what happens is it's going to go and look at, let's say, a set of index postings for A, a set of index postings for B, and look at the intersection for those. On the whole, it doesn't take a whole lot of compute, but it can add up on having to recompute. If this is like a frequently run query where you're constantly having to look at the intersection of A and B, what we can do is we can also materialize the index postings for the intersection of A and B. And that's effectively what a composite index does, is rather than having to compute this intersection and do it for every single query. Imagine if I run this query 1,000,000 times, I'm recomputing this 1,000,000 times. Wouldn't it be great if we could just compute it once, and then every single query just takes advantage of that? That, in effect, is what a composite index is going to do. Is when you define a composite of A and B, what we're doing is at the time of write, pre-compute and optimize for queries that have properties A and B. And then that way, on the read path on the query, it minimizes the amount of queue and minimizes the RU charges for such a query.
And it's sometimes staggering how much it minimizes it. I've seen the difference in some queries, and it's just you can go from like 1,000 RU to like 10 in some queries. I've seen it, just insane.
And it really adds up a lot. Like if you do now, imagine if I run this query 1,000 times per second. Well, you're saving that 1,000x that every single second. I'm going to take a peek in case if you have any questions, please add them into the chat window. I'm happy to entertain them. Like Tom or any of the other folks, feel free to add to it. And then what we'll do is we can make this a live running series. We'll continue to talk about Cosmos DB's backend and follow-up episodes. We'll also drill in a little bit more on the replication, HA, and change feed, since each of these is a rabbit hole on its own.
So I'm still working out schedule for the rest of the calendar year here. I got most things filled up, but I got about 3 spots left for the end of the year, and then we're going to take some weeks off. We got holidays coming up, November, December, of course. There's conferences happening again. NDC Oslo, and I will be in Oslo end of November. Haven't figured out. I was toying with the idea of doing a show remotely at NDC, but honestly, the logistics behind it is just, I think, a little too crazy. So
I see.
and also,
whenever we want.
It would be like 10 o'clock at night there too, a little late. So, but yeah, we can come back. Well, we'll get you scheduled back, and maybe people can come and ask some questions, either about stuff we talked about today, or you can go back and look at episode 20, where all of this started, and see if you got questions there. Yeah, let's do that. We can come back, and
for anyone watching after the fact, feel free to leave a comment once this video is posted and recorded. And yeah, we'll make this a live or living and evolving discussion.
That sounds good. That sounds cool. Cool. All right. Well, thank you everyone for joining us this week. We had Azure Serverless Conf yesterday and early this morning. You should be able to go and watch some of those sessions on demand if you missed any of them at AKAMS/Azure Serverless Conf. I'm thinking at least the Americas session should be up. It's only about 24 hours, sometimes less. But also, we've got a ton of on-demand sessions available there as well. So please go and check us out, or check out all the great sessions. There was some fantastic sessions yesterday. The keynote was amazing from the .NET community guys, James and John. They showed all the ways that they basically do everything. All their content production and everything is all done using serverless technologies. Dolby was showing how they do signal processing, all serverless. There was just too many. Lots of great sessions all yesterday. So come check those out. AzureServerless.com. We've also got a new user group. Had our first user group meeting a couple of weeks ago. We'll be scheduling a new one for end of October. That'll come out in the next week or so. But anyway, feel free to come and sign up and RSVP, or at least get reminders when we get our next user group meeting scheduled at AKAMS Cosmos DB user group. And then, of course, hey, if you got any show ideas, I do have some slots left for the end of this year. Feel free to just hit us up on Twitter at Azure Cosmos DB. I do see a question. Oh, just a comment from an old friend here. Great explanations, Andrew. Very clear. Love your insights. Yep, definitely. Always good. Always good, Andrew. So that's it. Next week, folks, I've got, we'll have Deborah Chen back. She was with us a couple weeks ago talking about all the autoscale stuff. She's going to give us a sneak peek into hierarchical partitioning, which is something I'm really excited by. In fact, if you're building SaaS applications or are using synthetic partition keys today, this is something you should definitely learn about and check out and see what we're building around that. So that's it. Thanks again, Andrew. Appreciate you coming by. Good seeing you again.
Cool. Awesome. Thank you, everyone.
All right. Thank you, everyone. See you next week. Bye-bye.